Mm, Assalamu alaikum. Welcome, students. Let's do a quick recap of the previous lecture. Uh, in the last lecture, we started the topic of the Laplace transform, which is the tool used to convert the time domain function into its equivalent frequency domain function or vice versa. Uh, then we discussed the Laplace transform of the basic functions. Then we explored the different theorems that exist in the Laplace transform. And then we commented that we hardly invoke the Laplace transform integral, rather, we use the Laplace transform table along with Laplace transform theorem to find the Laplace transform or inverse Laplace transform of complex looking signal by converting them into the simpler functions. And finally, we were discussing a method known as partial fraction method, which is used to convert the complex looking frequency domain function uh, into its simpler components so that we can use Laplace transform table or Laplace transform theorem to write directly the time domain equivalent of those functions. So actually, uh, we were discussing the case different cases that exist in the partial fractions. Uh, in the last lecture, we completed the case one, which is the roots of the denominator of f of s are real and distinct. And under this topic, we uh, explored an example problem. Uh, Now let's move towards case two, which is roots of the denominator of f of s are real and repeated. Mm. Uh, Consider an example under this topic or case. F of s is equals to 2 over s plus 1 over s plus 2 whole square. Here you can see we have the root, this root s plus 2 with power of 2. So this root is actually the repeated root. Now this root will generate an additional term in the partial fraction. Let's see how we write the partial fraction under this case. Writing partial fractions of the factors. Uh, f of s is equals to a over s plus 1, just as we returned in the previous case, and plus b over s plus 2 whole square, this whole factor, and plus c over s plus 2. Uh, just see the additional term that resulted due to the repetition of s plus 2. Mm. Now, if we have power 3 here, then it will result in an additional term uh, d over s plus 2, and this will become c over s plus 2 whole square, and this will become b over s plus 2 whole cube. Hmm. So evaluating constants a, b, and c uh, for the partial fractions to be equal to f of s. Now evaluating constants a, b, and c for all of these factors to be equal to this term. So equating the factors with the function 2 over s plus 1 s plus 2 whole square is equals to a over s plus 1 plus b over s plus 2 whole square plus c over s plus 2. Now it will become our equation 1. Now multiplying equation 1 by s plus 1, just as we did in the case 1 for evaluating the value of a. Multiply this equation by s plus 1, and then put s is equals to minus 1 in the resulting equation. So equation 1 will become 2 over s plus 2 whole square is equals to a plus b into s plus 1 over s plus 2 whole square plus c s plus 1 into s plus 2. Now put s is equals to minus 1 for uh, sorry, at s is equals to minus 1, this equation will become uh, 2 over minus 1 plus 2 whole square uh, is equals to a plus this term will become 0, and this will also become 0. So s a plus 0 plus 0, resulting in a is equals to 2. Now for evaluating the factor b, we will apply the same method. Multiply this equation by s plus 2 whole square and put s is equals to minus 2 in the resulting equation. So multiply equation 1 by s plus 2 whole square and put s is equals to minus 2 in the resulting equation. So it will become 2 over s plus 1 plus a s plus 2 whole square over s plus 1 plus b plus c s plus 2. Now put s is equals to at s is equals to minus term. The both of these terms will become 0. So 2 over minus 2 plus 1 is equals to b, and b will be equals to minus 2. Now for evaluating the factor c, what we will do, we will derivate the, will this equation, make it equation 2 with respect to s, and then we put s is equals to minus 2 in the resulting equation. So just write, for evaluating value of c, uh, we derivate equation 2 by s, uh, oh, sorry, it should be with respect to s, and then put s is equals to minus 2 in the resulting equation. So derivating it with respect to s, uh, 2 over, I'm sorry, I think I committed a mistake. Actually, it should be 2 over s plus 1 is equals to this term, and this term. Derivating this equation with respect to s, it will become minus 2 over s plus 1 whole square, which is the derivative of this term, and this will become is equals to a will apply u over v function. I hope you studied it in the second year maths. A s plus 1 s plus 2 u, derivative of this function s plus 2 into 2 minus this function, derivative of this s plus 2 whole square into 1, and finally this will become s plus 1 whole square plus derivative of this term will become 0 since it's the constant part, and the derivative of this term will become c into s, derivative of cs is c, and c into 2 is again constant, and derivative of this term will become 0. So here we will have the only constant term c. Now simplify this equation, minus 2 over s plus 1 whole square is equals to a s square plus 3s plus 2 into 2 minus s square plus 4s plus 4. This will become s plus 1 whole square plus c, minus 2 over s plus 1 whole square is equals to a 2s square plus 6s plus 4 and minus s square minus 4s minus 4. This gets cancelled. S plus 1 whole square plus c. Uh, this will become minus 2 over s plus 1 whole square is equals to a s square plus 2s over s plus 1 whole square plus c. Now at s is equals to minus 2, this equation will become c is equals to minus 2 over minus 2 plus 1 whole square minus 2 minus 2 square plus 2 into minus 2 and this will become minus 2 plus 1 whole square. This will result in c is equals to minus 2. Now, so the partial fractions will become f of s is equals to 2 over s plus 1 minus 2 over s plus 2 whole square minus 2 over s plus 2. Now, taking Laplace transform on both sides of this equation, taking inverse Laplace transform. Now, we know the Laplace transform of 1 over s plus a to be e minus at, and similarly the same formula can be applied for this term. Now for this term we have to apply the frequency shift theorem as well as the Laplace transform of t, which is 1 over s square, which is 2 units shifted in frequency. So we will use the Laplace transform table plus the Laplace transform theorem to find the inverse Laplace of this factor. So f of t will become f of t, f of s will become f of t, and this term will become f of 2 e minus t uh, minus 2t e minus 2t and minus 2e minus 2t, and finally u of t in the bracket. This is the inverse Laplace of the f of s uh, under case 2. Now let's move towards case 3, which is roots of the denominator of f of s are complex or imaginary. Uh, Now consider an example. Under this case, consider an example. F of s is equals to 3 over s into s square plus 2s plus 5. You can find out the roots of this quadratic equation. Roots of this equation are s is equals to minus 1 plus 2j and s is equals to minus 1 minus 2j, which are uh, the complex roots. So let's see uh, how we can write the partial fraction under this case. Write, sorry, writing partial fractions. Here f of s is equals to a over s plus bs plus c over s square plus 2s plus 5. You can see the way we have written the partial fractions of the function in case of complex roots in the denominator polynomial. Uh, so now evaluating these constants a, b, and c. So writing a statement evaluating constants a, b, and c for these partial fractions to be equal to this function f of s. So equating these partial fraction with this function, just as we did in the previous cases. So 3 over, sorry, 3 over s into s square plus 2s plus 5 is equals to a over s plus bs plus c over s square plus 2s plus 5. This will become equation number 1. Now, to find out the value of a, we will multiply this whole equation by s and then put s is equals to 0 in the resulting equation. Uh, Multiply equation 1 by s and then put s is equals to 0 in the resulting equation. Uh, the 3 over s square plus 2s plus 5 is equals to, this will become a plus bs plus c into s over s square plus 2s plus 5. At s is equals to 0, this equation will become 3 over 5. It will become 3 over 5, and a plus this whole term will become 0. So the value of a is 3 by 5. Now for evaluating b and c, we multiply equation 1 by s into s square plus 2s plus 5. We will multiply this whole equation by the denominator of f of s. So equation 1 will become mm, uh, 3 is equals to a s square plus 2s plus 5 plus bs plus c into s. Put a is equals to 3 by 5 as we have evaluated the value of a. So 3 is equals to 3 over 5 s squared plus 2s plus 5, and this will become bs square plus cs. 3 is equals to 3s square over 5 plus 6s over 5 plus 3 plus bs square plus cs. Now, combining the coefficients of the similar power, 3 is equals to 3 over 5 plus b into s square plus 6 over 5 uh, plus c into s plus 3. This will become our equation number 2. Now, comparing coefficients of the powers of s in the left hand side and right hand side of the equation 2. So, write in a statement comparing coefficients of the powers of s in LHS and RHS of equation number 2. So we'll have here the coefficient of s square is 3 by 5 plus b, and the coefficient of s square here is 0. So 3 by 5 plus b is equals to 0 will result in b is equals to minus 3 by 5, and the coefficient of s here is 6 by 5 plus c, and the coefficient of s is 0 here. So 6 by 5 plus c is equals to 0, and it will result in minus 6 by 5. Uh, now we have evaluated all the constants, so write the partial fractions. Uh, so partial fractions will become f of s is equals to 1 by 5 or 1 over s. Don't misunderstand this. This is s and this is 1 over 5 minus 1 over 5 3s plus 6 over s square plus 2s plus 5. Uh, Now we know the Laplace transform of this factor 1 over s, which is u of t, but we don't know the Laplace transform of this function. So we will apply some mathematical procedures to convert this factor into the simpler terms so that we can use the Laplace transform table. So first step is to make this quadratic equation a perfect square. So write a statement making a perfect square uh, in the denominator polynomial. So f of s will become 1 by 5 or 1 by s. minus 3 by 5, uh, taking 3 out of this factor, it will become s plus 2 and s square plus 2s plus 1 plus 4. Uh, this 5 can be written as plus 1 plus 4. Now we know this quadratic equation can be written in the perfect square form, which is s plus 1 whole square. So writing it down, uh, f of s is equals to 1 by 5 1 over s minus 3 over 5 s plus 2 s plus 1 whole square plus, and this 4 can be written as 2 square. There is a reason of why I am writing this way. Uh, it will be evident in the next steps. Now divide this 2 into plus 1. Uh, it will become f of s is equals to 1 by 5 1 over s minus 3 by 5 will become s plus 1 over s plus 1 whole square plus 2 square. Now divide the factors uh, uh, from here. So f of s will be 1 over s minus 3 by 5 s plus 1 over s plus 1 whole square plus 2 square plus 1 over s plus 1 whole square plus 2 square. Uh, Now we divided the LCM from here, so we can write it down as s plus 1 over this term plus 1 over this term. Uh, Now we know that the Laplace transform of the cos function is s over s square plus omega square. So if I shift this frequency by an amount a, this will be represented by e minus at in here. So e minus at cos omega t can be written as s plus a over s plus a whole square plus omega square. Here you can see this term is exactly equals to this term, with a is equals to 1 and omega is equals to 2. So I can write this term while taking inverse Laplace transform of this function. Similarly, for this term, we know that the Laplace transform of sine omega t is omega over s square plus omega square, uh, and e minus in a similar way just as we did in here, e minus at sine omega t will become omega over s plus a whole square plus omega square. So this denominator is same as the denominator of the cos omega t, but here we have omega and omega is 2. So what we will do, we will make the numerator omega by multiplying and dividing the factor by 2. So now taking the inverse Laplace transform of above equation, taking inverse Laplace transform, this will become f of t, and this will become 1 by 5, 1 over s will become u of t minus 3 by 5. This will become e minus t. The value of a is 1, e minus t cos 2t, and it will become e minus t sin 2t. So taking out e minus t from both of these factors, so this will become e minus t cos 2t plus this half 1 by 2, 1 by 2 sin 2t, and u of t in all of these terms. So this is the Laplace transform or inverse Laplace transform of the function under case 3. Mm, Now we have covered all three cases that exist while evaluating the inverse Laplace transform of a function. Now let's summarize the discussion. In case 1, when the roots of the denominator polynomial are real and distinct, then we write as many partial fraction terms as the number of roots in the denominator polynomial. For example, we have 2 over s plus 1, s plus 2, s plus 3. So, sorry. So we will write the partial fraction as a over s plus 1 plus b over s plus 2 and c over s plus 3. We will write as many partial fraction terms as the number of roots in the denominator. Now, in case 2, when the roots of the denominator, sorry, we also saw that how to solve for the values of a, b, and c, and how to find the inverse Laplace transform under the case 1. Now, in case 2, when the roots of the denominator polynomial are real and repeated, then we write as many partial fraction terms as the total number of roots in the denominator polynomial, considering the number of repetition to be the number of roots. What I am trying to say is, let's say here we have 2 over s plus 1, s plus 2 q. So we will write uh, this s plus 2 can be written as s plus 2 into s plus 2 into s plus 2. So we have 4 roots in the denominator. So we will write the 4 partial fraction terms. But the procedure is a over s plus 1 plus b over s plus 1 whole cube plus c over s plus 1 whole square, and plus sorry, it is plus 2 and it is 2, and d over s plus 2. Then we saw under the case 2 how to solve for the inverse Laplace transform. Now in case 3, and finally, when the roots of the denominator polynomial are complex or imaginary, then we write as many partial fraction terms as the number of roots in the denominator, except the complex roots are combined to yield a quadratic equation, and then we write a single partial fraction for the resulting quadratic equation in a manner that discussed earlier in this example. Here you can see uh, we have actually three roots. Two of them are complex and one is the real. So combining these two complex roots into this quadratic equation and make a single partial fraction for this term, and the partial fraction for this term will become this. Uh, now that was all about the different cases of the Laplace transform. Now let's end our lecture here, and we will continue further from here in the next lecture. Thank you very much. Allah Hafiz.